Hello everyone, my name is Yao Chen, and I'm from the Advanced Digital Sciences Center. Today I'm going to share with you one of our practice on heterogeneous clusters, which is named as HaoCL. This work is supported by the Alibaba Group with their Alibaba AIR funding, and it's a collaboration including ADSC, Alibaba, A-Star, NUS, and the University of Illinois at Urbana-Champaign. With the increasing volume of data to be processed and the higher complexity of workloads in modern academic and industrial applications, large-scale heterogeneous computing clusters have become an attractive solution that offers both massively parallel computing capability and large storage capacity by integrating traditional multi-core CPUs, many-core GPUs, and power-efficient FPGAs into the high-performance computing systems. Modern scientific applications usually consist of a large number of subtasks that have different hardware resource preferences in order to optimize either the performance, power consumption, or monetary cost. However, power consumption and cost make it impractical to equip each node in a cluster with all types of accelerators. An ad hoc assignment of these subtasks to nodes without holistic deployment information about all accelerators across the cluster inevitably lead to serious underutilization. None of the existing approaches provide both heterogeneity-aware and performance-oriented scheduling in an automated or user-guided manner. Instead, they usually adopt a static and heterogeneity-oblivious mapping between tasks and the hardware resources. Besides, FPGAs are moving into cloud computing as well. However, previously proposed frameworks only consider CPUs and GPUs. There are few studies on how FPGAs can be utilized to improve the energy efficiency. At the OpenCL and OpenACC provides cross-platform manner so that one copy of source code can run on different OpenCL compatible devices. We still lack of solutions that can provide an efficient and easy-to-use abstraction of a heterogeneous cluster. Aiming to solve the issues above, we propose HaoCL, which adopting OpenCL and designed with three major functional components. First of all, it contains an OpenCL wrapper library with an extendable scheduling component. Secondly, a communication backbone that takes care of the message delivering among the different nodes. And a node management process that runs on each device for the actual execution of OpenCL API calls. Let's look into the details of the different functional components. The OpenCL wrapper library adopts identical names as standard OpenCL APIs. It also takes care of the creation of the data packages. We extend the original installable client driver to be compatible with the front-end wrapper layer and the communication backbone for remote API calls forwarding, so that each call to the standard OpenCL APIs can be executed in the form of implementation according to the remote device and the vendor drivers. The task scheduling component on the host node is aware of the runtime information of the accelerator nodes. Well, need to note here, in the current version, it delivers the kernel tasks to the device nodes based on the user's instruction. However, it is designed in an extendable manner so that it can be upgraded to an automatic scheduler based on the application, which collects the runtime profiling information from the cluster to enable more accurate heterogeneity-aware task scheduling. The communication backbone is built as a network among hosts and devices for data and command transfer. We adopt the Boost library because of its stability, scalability, and asynchronous data transfer feature. We also leverage a mapping mechanism to address the message delivering among multiple different accelerator nodes, so the backbone maintains the mapping with the device IDs. The node management process is designed as a daemon process that runs on each device node, and it receives commands from the scheduler. We'll need to note here that node management process for the FPGA nodes also determines if the call could be executed based on the FPGA configurations. We conducted our evaluations on the Alibaba Cloud with a total number of 20 nodes. Each of the nodes is equipped with a Xeon E5 CPU, and 16 of the 20 is equipped with an NVIDIA Tesla P4 GPU, and the other 4 is equipped with the Xilinx VU9P FPGA. We choose the benchmarks from the benchmark site Rodania and SHOC, and each of the benchmark we chosen is with a different input size. The end-to-end evaluation is performed by scheduling the tasks on different tabs and different numbers of nodes, and is denoted as GPU, FPGA, and GPU plus FPGA configurations. The presented results are normalized to the unit configuration, which is either a single GPU, single FPGA, or GPU plus FPGA with a local OpenCL environment. Our framework can achieve a linear performance improvement compared to the single node implementation when the number of the nodes scales. However, the performance of the benchmarks also depends on the computation and communication pattern of the benchmarks. We also compare our results to the framework called HaoCL. Comparing to the HaoCL, our framework shows a better performance improvement when the nodes of the system scales up. In addition, our framework also supports heterogeneous node types, which contains both GPU and FPGA. We then choose MM and SPM way for the heterogeneity evaluation because of their complexity of data transmission and the different requirement of efficiency. The performance is normalized to a system that is configured with a single GPU plus FPGA node. The matrix multiplication kernels on different devices are kept the same, while the data partition of the SPM way is allocated on the GPU nodes, and the computation is performed on the FPGA nodes. We can observe the performance improvement when the system scales, and the performance also varies with the different system configurations. Matrix multiplication is also selected for the breakdown analysis for our framework. Since our node management process manages all the nodes with the same behavior, so the CPU, GPU, and FPGA nodes have the same overhead of communication and local environment setup. The system initialization time is negligible when compared to the data creation, computation, and data transfer, so it is omitted in this figure. We could learn that the communication and data creation time increases with the data size, while the ratio of them actually decreases. This demonstrates that our framework is effective in terms of fully utilizing the computational capacity of the HPC clusters. Thank you all for listening to my presentation. Please feel free to contact me with any questions.